there has been 2 decades of consistent coding, fundamentals, uh, aligning skills to what the industry needs, right? That has led to this. And consistency will always compound, and that will lead you to where you really want to be. So like the career has a trajectory, no? You're studying right now. In 3 to 4 years, you will be in a job. If you're second year, so if you're final year, yeah, it's high time. Buckle up. So you will be entering the workforce soon, right? And then you will want to have a career trajectory. You want to start your work, learn, grow, lead a particular project, start leading teams and grow. So there's a trajectory to it. Similarly, industries also have trajectories. How did semiconductor grow from discrete transistors to multi-billion transistor SoCs, wafer scale chips that are coming out, right? From a single function chip that does, let's say, a single microcontroller, right? It takes instruction, generates the required output. Now to a full system where you have all serial protocols, you have USBs and PCIs, Ethernets, visual processing units, CPUs, memories, everything on a single chip, right? So multiple entities, full chips getting integrated in a single wafer in a single tape-out, right? From Southeast Asia-centric manufacturing to globally distributed value chains, right? The lithography machines coming from one country, the design cycles happening across different geographies, across different domains. For a single chip right now, for example, if I give an example, right? Each and every chip in the world right now has a team based out of India designing it, working on it, and taping it out. No, not a single product. The system architectures are becoming increasingly complex, not just in terms of what different types of features you want to put in, but the power requirements, the processing speed requirements. So there are a lot of challenges. So if you see the growth, it is exponential in terms of what the complexity is going in. Now with AI data centers, the amount of throughput that needs to go through one chip is ridiculous when to the point where we were at, let's say 10 years back, right? So this clearly means there's a lot of work that has to go in fundamentally. There has to be a lot of job roles that will grow exponentially along with that. Again, in terms of strategic nature of this domain, it is not just that as a country we are moving up the, from a talent provider sort of, we are growing up the value chain in terms of what all things, it is almost mandatory for us, it is imperative that we have this capability within the country, right? For power, automotive, connectivity, defense. The foundation to your, national competitiveness for your DRDO, for your ISROs, for all your satellites, right? All those systems, it is imperative that the value chain stays within the country. And for that, this means the domain is of very strategic importance, and it will grow. And because the domain itself is growing, it is it is very important that engineers start focusing on the domain and start to see the value behind this, not just in terms of the money it generates for you, which is definitely there, but also the depth and the way you are able to contribute to the national ecosystem. Right? So fundamentally, if we break it down, what is a chip? When we say a chip, it's a set of transistors, logic gate, the transistors combined into a gate, the gates combined into an IP block, right? IP block, you can say, okay, a USB is an IP, a CPU is an IP. all these different types of IPs, a combination of gates that functions a certain way. It's an IP. Different types of IPs combined on a single chip to form a system on a chip. It's still on the wafer. Till system on chip, we are still on the wafer. Then the packaging. The system on a chip is transitioned or transformed into an actual packaged product that you place on a board, and that board then goes, right? When it goes to the board and it is really into a product, that then it becomes user facing in a way. Now let's break down the life cycle of a chip. So first thing, chip, right? Application, etching, lithography and all that. 3 to 4 years before that, rather, right? The first stage, architecture stage, essentially defining what you want to. Let's take an example. I want to make a security camera chip that takes my camera visual inputs, processes those visual inputs on the chip, identifies what sort of things are moving and what are the back and forth within that frame or across frames, stores it and does something essentially applicable to your security cameras, your drones, and all these defense ecosystems, right? So you want to define ye chip kya karegi, right? Once you clearly define it, then you realize, oh, I need to put these many things in it. Then comes the design cycle, where you do the RTL design, design verification, design for testability. We'll just spread this out and we'll look into it further in the coming slides. These are individual roles. So each and every block mentioned is a complete set of domains where there are real jobs, right? RTL coding, Verilog, design verification, system Verilog, DFT, scan, ATPG, BIST. So this is the front end, the soft design of an IP. Then comes the physical design, the back end, right? So finalize this functional architecture of a chip. How do you place it within the actual physicality of the chip? जैसे CPU, let's say, memory से read write कर रहा है, okay? Simple terms में. क्या वो रीड राइट सक्सेसफुल हो रहा है? ये हमने डिटरमिन कर लिया. लेकिन अगर चिप के ऊपर सीपीयू एक कोने में प्लेस कर दिया और मेमोरी बिल्कुल दूसरे कोने में है, so the amount of time it takes for the read writes to happen really slows the net performance of the chip. So the physicality of the chip is also engineering, right? And it is complex in nature. And so the idea is not to make you understand how do you do physical design, how do you do DFT or DV, but to initiate this concepts that you have these terms in your mind, right? It goes to an OSAT, which you might have heard in the recent news that a lot of OSATs are coming in. They assemble that chip, package that chip, and finally it is put on its own. Even then, when you have the packaged chip, it is useless. You can use it for decoration, because then you have to integrate it on the board with the firmware, right? The board design, high-speed design, these are again carriers. So this journey, right? Each stage is a full discipline where people spend decades working on it, right? Each with its own unique technical challenges. And now we'll sort of try to break this down further in terms of front end and back end. Okay. So when we say front end, it means whatever I'm making, is it functionally correct? ये चल रहा है क्या ठीक से? जो मैं बनाना चाह रहा था, क्या ये जो बना है चिप या जो सॉफ्ट आईपीज मैंने बनाए हैं फंक्शनली वही है जो मैं बनाना चाह रहा था, राइट? So you have the architecture, RTL design, this in Verilog, system Verilog, VH verification, which the code domain previously, where I am coming from. So the functional validation or verification of this design through simulation. So Verilog, you can you might be already knowing system Verilog is like to C++ what Verilog is to C, simply put it, right? So you essentially understand the design intent कि design क्या करना चाह रहा था, जो designer ने बनाया वो क्या सोच के बनाया और actually में क्या होना चाहिए, and you verify it. Then comes formal verification, which is a mathematical proof of correctness of the design. So for every one design, 3 to 4 DFT engineer opportunities. When we say, okay, I want to design, that's not the only portion of the job role, right? There are hundreds of job roles beyond that. Formal does the mathematical proof of correctness. Emulation does the same simulation, but in a hardware accelerator. Don't need to understand that. That's absolutely okay. It's just that it does some of these simulations much faster than on typical EDA tools. But don't worry about that. So fundamentally, I just want to bifurcate and for you to see that how many different types of activities are done. Right. Then comes DFT, design for test. DFT is sort of add-on design logic that you put. In layman terms, if I can tell you, right, it is sort of like the service roads on the main highways. Right, service road, it is engineering. It is still the same structural correctness, functioning of the design that you do. It's just that you, once the device is made, you need some lanes to be able to see, is the main road fine or not? If the main road is broken, how will you reach that point? You need a service road for that, right? So that sort of add-on design logic is added. This is the front end, the logical world. Then we come to the physical world. Whatever you have made, can we actually manufacture it properly? So then we transform this RTL into gate level netlist using libraries that are provided from the foundries. We do flow planning, as I mentioned, CPUs, where is the memory sitting, where are the IPs sitting within the chip. Placement and routing, connecting all these things within the silicon. Timing analysis is some portion of the memory which I was assuming to be near one portion is actually being utilized by some other guy, and that other person is suffering, other IP is suffering, right? So you have to carefully analyze whatever I have made is meeting my timing. All the blocks are able to access things properly. And now, because low power devices, you have a lot of power analysis. If a lot of heavy memory or sort of core logic is running in a confined space, it is bound to generate heat, right? So electromigration checks, you have thermal validation, you have IR. So each and every of this thing, again, from the same standpoint, its own specialization, is its own domain in complete each and every point or keyword here is its own career that you can take. Right? And finally, the sign off, where we say, okay, everything is fine, please tape out the chip. So now, this till here, you didn't actually have the silicon. You were just, this is all pre-silicon activities. Now we reach the silicon activities, which is called the fabrication. This I'm very sure most of you would be aware or would be, sooner be made aware. So lithography, doping, etching, the metal layers, and the wafer probing. Right? But yeah, so this is the physicality aspect where the job roles in terms of process engineers, you would have fabrication, the people who operate these complex machines, right? These are not blue collar jobs. These are proper engineering jobs, need as much complexity as any other we saw in the previous slide, right? So after these stages, you have a silicon wafer, fundamentally. And here you're operating essentially at atomic scales, right? This is fundamentally where your physics portion comes into picture. Now the third stage, not the final one. So the packaging and OSATs that are predominantly now increasingly more coming in India, right? So the whole wafer, you cannot make a product. You need to first dice the wafer, precision cutting at that scale in individual dies. Those dies have to be attached to a substrate, is its own domain. Interconnect, wire bonding, checking whether the things are proper, encapsulation, packaging, and finally testing. The final test that we see is actually done by the previous activity on design for testability. So they generate patterns which are used by the OSATs to actually test the end product, the wafer that is there, right? So you have packaging engineers, test engineers, reliability engineers, failure analysis engineers, right? These are all again specializations on their own. And now we're talking about a 2D world, and we have moved beyond 2D world in 2.5D interposers, 3D stacking, right? There's only so much space on the chip. How do you increase the density further without going lower in the technology node, right? You simply add more layers on top before packaging or during packaging, right? Uh, Essentially, like you have a single house, you move to a bigger city, there's less space, you have 3-story individual houses, there's further density in the city center, you have multiple 4-story houses collectively together as a society, right? And then you have go even further, you will have G plus 30, G plus 40, right? Structures. So essentially that, but at the chip level, coming with its own set of complexity and the need of its own set of engineers. Now we may think, okay, my OSAT and chip in a black sort of packaging that we typically see is ready. Engineering is done. At least electronics side we are done, but it is not. That's only around 70% of it, right? This you cannot do anything with it. You can place it onto a wall and decorate it. That's about it. Without modules, boards, firmware, it is useless. It is simply an inactive potential that you can have a look and have, just look at it. You cannot do anything with it. So unless you integrate these with power supplies, with passive components, then design the PCBs, multi-layer routing, impedance control, power distribution, integrity check, manufacturing, that gives you the actual hardware that goes onto your phone, your laptop, and all these things. Even then, it is useless. There is still the firmware development that is to be done. Essentially, layer that brings to the hardware. What the chip is, how does it talk to each other within the chip, how does that communication happen? All that is done by the firmware engineers, right? Board support package, uh, device drivers, RTOS. So these are all again domains in which specialization can be done. So all these technology sort of nodes that we see now, we now at least I expect you to see that, okay, this is not a single chip, right? And we need a certain set of engineers to just do that portion. It is 10 and 15 different domains, each having its own 10, 15 different specialization, right? Multiple stages, multiple teams, multiple companies to make one chip. So all these technology creates your technology roles, the roles that you all can target. Engineer, yield optimization engineer, package technology engineers, engineers. These are the roles. And then you zoom out a little more. Then you have system and embedded engineers, firmware development, BSP engineering, FPGA prototyping, your system integration, uh, the bridge between the hardware and software domain, right? Then you have another set of job roles, which are the tools and EDA companies that actually the tools from which are used to do all these previous tasks. For example, Cadence, Synopsys, Mentor tools. These are all companies, again, where the software infrastructure of the tools used to simulate designing, as of now, we are very good at. The services and consulting, India is very good at. But, sorry, but this sort of is only very small, one portion of the value chain. Now we see in terms of the actual manufacturing, fabrication, OSATs, embedded hardware work, right? Predominantly that was not there in the scope till very recently. Now increasingly ever more, there are people, companies with the central governments, all state governments, putting in a lot of effort and a lot of focus to grow these domains. So this means the actual number of core engineers required are a lot more now than what previously were, even with AI, right? And obviously that will be a topic in your mind. I've purposefully not put AI in any of the slides, right? And I'll come to that, the core reason why I've done that. So now this is all nice, but your question will be, कि, अच्छा मतलब करना क्या है अभी, right? So your fundamentals stay the same. Your coding skills, mathematical skills, physics fundamentals are the same, right? That is what, as of now, if you're good at C, C++, System C, have a decent idea about digital electronics. If you're want to go into the code domain, an absolute deep understanding, it should be intrinsic to you, as 1 + 1 = 2 is intrinsic to you. That should be that much in, deep inside, embedded inside your heads. The digital design, embedded systems, board and systems, manufacturing, FPGAs. So these are the skills, fundamentals, which connect you to all those job roles. Verilog, VHDL, timing analysis, constraints, microarchitecture concepts. How does a microcontroller function? How does a CPU function? How are all these serial IPs do they function? As of now, even on the embedded side, right? C++ programming, it is the fundamental each and every person should know, irrespective of the domain. And you should have deep understanding of it, not just how to write the code, but what happens behind it. How it is processed. When it generates an object file, what it has, right? If you're talking about an electronics engineer or a design engineer, you should fundamentally have an understanding that what does my object file actually contain? To that level of depth, don't remain at the surface level, right? Go deep, have that curiosity. Linux is important, the Linux kernel, Linux drivers. How do the softwares sort of work and interact with the board? Like, don't just purely rely on, Arduino or sort of basic. So that are good stepping stones, right? But then go into the deep functioning, why it is functioning, how it is functioning, how my C code interacts and does switches on an LED, right? It's not that अगर मैं ये लिखूंगा, ये configure करूंगा तो मेरा LED जलेगा. कैसे हो रहा है? उसकी spec के अंदर जाओ. Real-time operating system, which is called RTOS, right? Hardware software interfacing. On the manufacturing side, you have semiconductor physics, which is important, material science, which is important, statistical process control, yield methodologies, and all these stuff. These are, fancy terms for saying resource optimization. You have your basic stats and DSP fundamentals. So these are the real subjects that you are learning, would be learning, have learned. Directly connect you to these. Because see, the college gives you those fundamentals based on which you need to realize and build and go deep based on your curiosity. Right? And so the fourth stage, so you have the digital design, embedded design, how it interacts with the software, you have the actual manufacturing of the chip, and then you have the board and systems, PCB design, tools, signal integrity, power simulations, high-speed designs. So the skills are very different, right? But the fundamentals are absolutely the same. How do we connect this in terms of the roadmap for each year, right? First year, moving into second year, focus on your mathematics and coding, C programming, fundamentals, go deep, basic electronics, circuit theory, your digital logic design. Sometimes it's in the third semester, and I understand that. So you gradually move on these layers. Year two, by the end of year two, you should have very strong fundamentals in digital electronics, Boolean algebra, microprocessors, basic computer architecture, signal system theory, data structures, algorithm. DSA is extremely important. All these are the real subjects that I have read, you will be reading or have read, right? It directly connects to the actual job. Now, core focus in terms of, so how this transitions into your actual job, that we'll see in, that is somewhere I think where the industry connect helps you, right? So building on top of that, Verilog, system Verilog, VHDL, or other HDL, Specman E, embedded C++, system C, right? For example, in India right now, there are only 3 companies which have some level of expertise in system C, and the market demand is so huge that even a person with 1 or 2 years of experience in system C, which actually knows this, has the basics of hardware and is very good at system C, you will have an excellent career there. Not that in the others you will not have in each and every of these domains. So that curiosity will help, right? By the end, so and also something that is what I have seen is missing as of now till now in people who are graduating is the actual protocol understanding. See, protocol is just a set of definition based on which a hardware functions. So essentially, it is not part of your core knowledge, the fundamental base, but at the same time, for all these domains, it really helps us you to visualize कि chip पे अंदर हो क्या रहा है. Right? SPI, I2C, UART, these are serial low speed protocols. You have PCI, which is high speed protocol, USB, Ethernet, MAC, SerDes, NVMe's. You must have heard NVMe SSDs. So that is nothing but a set of defined rule based on which an IP is made. Right. So by the end of year 3, you should be in a stage where you actually know the fundamentals and start connecting it to some actual physical hardware. And year 4 is when you, by the end of year 4 or beyond that, you need to go into deep specialization where advanced verification, if you want to move into verification, you should have advanced verification methodologies. For if you want to move into backend, physical design concepts, the low power concepts. For embedded track, if you want to go in, RTOS, what is RTOS, how it is done, have some hands-on. Device driver development, SoC architecture, Capstone project helps. Deep technical exploration helps. All this data is freely available on the internet, trust me. It is not some, fancy sort of knowledge base that is logged in. Each and everything is available right now. If you want to learn, it is free on the internet, open. Right. Now, from technology, we sort of transition into from the technology we transition into jobs, but jobs are not fundamentally guaranteed, right? That is predominantly determined by the market की क्या बिक रहा है, क्या बन रहा है, strategically कहाँ investment हो रहा है, वहां पे jobs बनेंगी, right? Semiconductor अलग से एक job role या अलग से एक industry नहीं है. It is actually the fundamental blood that runs each and every other industry, right? AI data centers, automotive, the revolution and the way the automotive growth has happened is because of in the EV growth, the charging infra, your ADAS, and all the battery management systems. That is deep semiconductor expertise that has gone on. 5G, 6G now, connectivity, the IoT improvements, edge AI coming in, V2X coming in, right? That is fundamentally semiconductor architecture enabling innovation at a in a logarithmic scale across industries, right? So if you see the engineering roles, the job roles follow the market. जो markets बढ़ रहे हैं, अपने आपको उन डायरेक्शन में प्रिपेयर करना है. Magically नहीं, fundamental concepts, right? Essentially, Once you align those two, you'll have a much better likelihood. Now, where are ground reality? So ये hypothetical नहीं है. Now we touch the ground reality in terms of where is India right now. In terms of design strength, the first portion of it, right? India is the world's largest semiconductor design workforce. And when we say world largest, not amongst the world largest, the world largest workforce of semiconductor design is India. Major GCCs, each and every chip that you see in the NVIDIA release, the AMD releasing MI series of AI chips, the H100s, H200s, Blackwells, magically US में बैठ के नहीं बन रहा है. Some of your seniors, some of your bosses are actually designing that. I'll give you an example. My batchmate, Tulika Gupta, and now my better half as well. So she is responsible for the entire backend for the most bleeding edge of chips that as of now are being made in Bangalore. AMD. So MI300, MI325, MI350, MI450. It's all the backend is governed, sort of directed and architected by her. Right? So it's not, these sort of roles are not inaccessible. Even, I'm not saying just initiation, being at the top of it, at the bleeding edge of it, it is has been done by your seniors, you can do it. There is nothing stopping you. But that based on your fundamentals, coding skills, pay special attention in terms of how do you align and really understand what you're doing in the labs. Right. So growth drivers, but these R&D centers, Bangalore, Hyderabad, Pune, NCR, and all these things, right? Why are these exploding? So there we are fundamentally, India is transitioning from a service to a product engineering powerhouse. AI, ML, chip design, the startup ecosystem in terms of manufacturing is not there, sure. But in terms of the fabless ecosystem, this means anything that comes before the fabrication, except for the fabrication and after the fabrication is being done in India, which is very good. So within 2 to 3 years, you will be at a stage where all these job roles will immediately open up for all of you. Right. Now, the manufacturing side ambitions, which are a little tricky beyond yours and mind control, to be honest. Right. That's because it needs millions and millions and billions of dollars, right? So a single, I'll give you some clarity. The camera SoC that we were initially talking about, right? A single camera SoC, the cost of architecting to fabrication to productizing that is close to 12 million US dollars, 100 crores for a simple camera chip. All that thing cannot be done without backup and support, a strategic investment from the governments, the India Semiconductor Mission, fabrication investments, fab investments are coming in, OSAT expansions are coming in. The supply chains are being diversified in terms of पहले चिप डिजाइन यहाँ हो रहा है, वो जा रहा है ताइवान से मैन्युफैक्चरिंग होके सिंगापुर जा रहा है, सिंगापुर में OSAT से टेस्ट होके फिर कहीं और जा रहा है, वहां पे पैकेज हो रहा है, वो पैकेज प्रोडक्ट वो जो चिप और बोर्ड चाइना में जाके किसी प्रोडक्ट में लग रहा है, वो जा रहा है यूएस और उसको हम खरीद रहे हैं फिर इनिशियली जिसको हमने बनाया. Right. So that is coming back. Right. So all those job roles are opening. And the career impact, right? There is a sustained growth even without, just keeping AI to one side right now. I know given the AI hype that is going on, but bear with me. So all these roles that we have discussed, all the way from front end, back end, OSATs, fabrication, are all growing. EDA tools, embedded, firmware is where developing yourself for the companies who are bound to do and make products and make investments for India's specific strategic needs. It will happen. It has to happen. There is no option. So this means those job roles will be there and will open up. So we do not lack talent, right? It is just about the talent that we have is now being aligned to market opportunities that are there. And this decade will really define our global semiconductor leadership, right? Uh, just to conclude, right, it all sounds like a dream or a delusion, but you have to be slightly delusional. Otherwise, you're doing something wrong. If you're not able to imagine this, if you're not able to imagine you making a chip right now in first year, second year, third year, or final year, you have to imagine yourself working in such a role, and you have to be slightly delusional. Just back that up with your fundamentals, right? Your technical depth, really investing your time, effort, energy, banking on the revolutionary.
So first I will thank you for your such a nice, informative, illustrative and focused on semiconductor, the current field. So we are thankful to you
It's an honor.
from behalf of Department of Electronics and Communication Engineering. And thanks to Bhim also that who organized this, who contact you. And we are sometime we will call you physically here in our
Absolutely.
college.
Absolutely.
ठीक है ना?
See, either you ask or and then I start asking. Okay. See, अजमेर क्या केवल मेरा कॉलेज ही नहीं, मेरा घर है, तो मैं वहां के भी पूछ सकता हूँ और बात कर सकता हूँ. अभी बैंगलोर में, that is another story, but yeah, anytime that you need me, I can drop by. But yeah, see, इस फोरम में अगर नहीं पूछना चाहते, LinkedIn पे आई एम अवेलेबल. You can take my phone number, ping me whenever I have time in a different setting. If you're not comfortable, you can connect. But the point is, right now we all have time here, 10 to 15 minutes. अभी जो interaction
अक्षय, अर्पिता.
So my name is Arpita.
Hi, Arpita.
So we want to know your experience in this journey of semiconductor industries.
Okay. See, सच बताना है या मतलब शुगर कोट करके बताना? Okay. See, I was not a topper, right? I was a good student with inquisitive nature, very strong at coding, didn't really main gaps that retrospectively I'm able to clearly see is लिखना, explain करना, marks लाना नहीं आता था. But the coding fundamentals, mathematical skills, digital electronics, and all your fundamental subjects conceptually बहुत strong थे. That is the key reason that helped me land my first job, right? So real ground, I'll tell you. Post 2010, went to Delhi for preparing for different job opportunities and just different walk-ins and all other things. So there was one opportunity. So you have to put yourself out there. Magically, आपकी जेब में नहीं आने वाला है. Okay, you have to stay strong, fundamentals, learnings across years. But उसके बावजूद भी job is not guaranteed from everyone, for anyone. You have to put yourself out there. You have to compete. When I went there for a particular job opportunity, it was an intern opportunity. Okay, a design intern. Okay, the pay package that they were saying was 10, 11,000, something like that. And there were 250 people. C, C++, basic coding, algorithms, and all these things. 20 people got selected for that internship opportunity. 3 were promoted the same day before joining. One had a master's from in design, VLSI. Another was from DC, and third was me. Based on my fundamentals, coming from the middle of the batch, I competed with thousands and thousands of kids and defeated them from all over Delhi, North India, everywhere. Everyone was competing there, even after that, only because of the strong fundamentals and strong coding skills. daily make it a habit that you are coding for at least 30 to 45 minutes and not just, printing stars and asterisks. Okay. If you have access, me, Bhim and other folks will figure out if we can, provide you with some relative. So especially on the some boards or some sort of those things where you can actually program those boards and see how your code interacts with the hardware. So that level of we didn't have even an advanced understanding of all these things, right? But the fundamentals were there. That will always stay with you. See, from there, starting my career designing IPs. I designed IPs, USB IP, something I designed, USB verification IP is something I designed. Worked on, then moved to Mumbai, lived in Ahmedabad for 3 years, worked on several SoC chips that goes into your calculators, advanced calculators that go into some of your, mobile phones if, S21 series, right? So the Exynos chips that goes into S21 series, I was working on that. For the display and the USB subsystems, I worked on that. So from that node, the later stage of my career, in terms of the business transition and all these things, so those are fundamentally that you may or may not right now relate, that may be your career path or not. So I don't want to dwell too much on that. But see, fundamentally, when you start your career and you have your first job and, just in the initial growth of your career, growth years of your career, that's the trajectory right now you want to focus on. Focus on your fundamentals. How do you crack your first job? Now, in terms of the opportunities that are coming in, right? A lot of, so companies you can divide into several buckets. You have product companies that design IP, that buy IP from other product companies and design SoC. Then there are companies who take this design of the SoC and do physical, the back end of it, that are their own companies. Then there are companies who take the final back-end completed netlist, the GDS2 it is called, and manufacture it, fabrication side. Then there are companies who take that, make the package. Then there are companies who make that package, put them on a board. Then further, who make the firmware, software layer. Then who actually make the product. Each and every stage, there are different companies. Right? If you start taking names, okay, you have Intel, Broadcom, Qualcomm, NXP, NVIDIA, AMD, Micron, Microchip. And then you have the sub companies who sort of supply a lot of interesting IPs, AlphaWave, you have ARM systems, you have all these companies, right? Then you have tool companies, which are Cadence, Synopsys, Mentor Graphics, Siemens, right? Then there comes the service ecosystem, where now recently the consulting ecosystem, which I'm part of, where we consult companies in terms of how do you make better your architecture, what sort of foundry nodes to select, right? And we sort of work on those things. Also, arbitration of people, learning, development, and all these things also that we do sometimes. And then comes your manufacturing part of it. That is more of a process engineering. You have